Hello everyone, myself Engineer Amul Gurde, lecturer from the Department of Civil Engineering, Praveen Patel College of Diploma Engineering and Technology, Bhimber. So guys, today we are going to start with our third chapter, that is permeability and shear strength of soil, which is included in your syllabus of geotechnical engineering. This particular chapter is weightage for 16 marks in your syllabus. So starting with introduction part. What is permeability? When any given soil mass consists of solid particles of various sizes with interconnected void space and other or any other liquid through its interconnected voids under gravity. This flow of water is very much important with respect to structures such as dam, foundation and settlement and consolidation. So whenever we are talking about definition of this, permeability of soil can be defined as the property of soil which permits the flow of water or any other liquid through its interconnected void under gravity. In other words, permeability is the case with which water can flow through it. So looking at below diagram, here different sizes of particles, cell particles are shown and voids also shown in between them, and you can see the water is flowing by from the voids present inside the soil. So why this is important, or why we can say permeability is that much important? So here are the various reasons or various points by which permeability is important. To calculation of seepage through the body of earthen dam and stability of slopes, calculation of uplift pressure under hydraulic structure and safety against piping, groundwater flow towards wells and drainage of soil, estimate of loss of water by seepage or percolating, especially inside unlined irrigation channel, etc. Determination of rate of settlement of saturated compressible soil layers. Low permeability will be suitable for coronal beds, embankments, to check the loss of water by percolation through earthen dam. High permeability will be useful for structural foundation, rail embankments and subgrade off-road, because pervious soil keep the structure stable during rain and thaw. Next one is laminar flow and turbulent flow. The flow of water through soil may be laminar or turbulent. In most of practical flow problems in soil, the flow is laminar. So what is laminar flow? The flow in which water particles are moving in a definite path or moving parallel without crossing the path of particles is called as laminar flow. So in first diagram you can see all the particles are moving in straight path, and it is called as laminar flow. And in second diagram it is turbulent flow. Turbulent flow don't have any definite path. The flow in which the particles of water do not follow a definite path while flowing and cross the path of each other is called as turbulent flow. So in second diagram you can see the turbulent flow. Here comes the Darcy's law. What is Darcy's law? For isotopic homogeneous soils under laminar flow condition, H. Darcy in 1856 established a law of rate of flowing through soil. This law is called as Darcy's law. It states that for laminar flow, the rate of flow or discharge per unit time is directly proportional to hydraulic gradient. So it can be written as Q is equal to KIA, where Q is discharge per unit time, A is total cross sectional area of soil mass, I is hydraulic gradient, small I is hydraulic gradient, which is equal to H by L, where K is Darcy's coefficient in permeability, V is velocity in flow, H is differential head of water, and L is length of sample. So for establishing this formula, we can use the following diagram. You can see here the two different reservoirs are placed over there, which are having a manometer attached to them, from which we can get the height or head of the water, and a single porous pipeline is attached to it. Single canal we can see attached to it. So H1 is the height of height of water level in first reservoir. H2 is in second one. So total H is equal to H1 minus H2. Moving further to coefficient of permeability. What is coefficient of permeability? As we see now, Q is equal to KIA. Hence we can write it as V is actually a Q upon A. Velocity is discharge upon area. So here we can get the value V is equal to Ki. In above equation, when hydraulic gradient is unity, K is equal to V. Thus the Darcy's coefficient of permeability or the coefficient of permeability is defined as the average velocity of flow that will occur through the soil total cross section area of soil under unit hydraulic gradient. The dimensions of the coefficient of permeability K are thus the same as the velocity. K is usually expressed as centimeter per second, meter per second, feet per day, etc. So talking about limitations of Darcy's law, as we know, everything has a certain limitations. So Darcy's law also has certain limitations. It is not valid for all types of soil, but it is valid only for clay, silt and fine sand through which the flow is laminar. One, not valid for coarse grain as well as extremely fine soil, for example gravel, coarse sand and colloidal clay or silt, etc. It is difficult to predict exact value of Reynolds number. Some of the values demonstrated in Darcy's law are valid, so long as the Reynolds number is equal to or less than unity. But Scheidegger collected data show that the Reynolds number may vary from 0.1 to 75 for Darcy's law. Experimentally, it is found that the velocity and gradient relation give idea about laminar and turbulent flow. From there, the velocity of Darcy's law can be known. But in case of very dense or lightly compacted clay, it indicated that no water flows takes place, but all until head gradient reach some particular value. In this respect, no flow has reference to the limit of observation. Here are some factors affecting permeability. Very first factor is grain size. Permeability is approximately proportional to the square of grain size. The permeability of coarse grain soil is very large as compared to the fine grain soil. The permeability of coarse sand may be more than 1 million times as much of clay. Allen hasn't found permeability of filter sand having particle size between 0.1 to 3 mm can be expressed as K is equal to 100 into D by 10 the whole bracket ka square. Second one is void ratio. Increase in void ratio cause increase in permeability as the area available for flow increases critically. K proportional to E square. Third one is properties of pore fluid. Permeability is directly proportional to the unit weight of the pores fluid and inversely proportional to the viscosity of pore fluid. Unit weight of water does not vary, but the viscosity varies considerably with temperature changes. Fourth one is structural arrangement. The permeability is greatly affected by the structural arrangement of soil particles. Then stratification of soil. Stratification means formation of layers of soil during the deposition. The permeability parallel to stratification is greater than the permeability perpendicular to stratification. Fifth one is entrapped air. Entrapped air and organic impurities in the voids obstruct flow and cause a reduction in permeability. The sample for permeability test should be completely saturated. Sixth one is absorbed water. The fine grained soil have a layer of absorbed water strongly attached to their surface. This absorbed water layer is not free to move under gravity, it causes an obstruction to flow of water in the pores and hence reduces the permeability of soil. Seventh one is shape of particles. The permeability of soil depends upon the shape of particles. Angular particles have greater specific surface area as compared to the rounded particles. For the same void ratio, the soils with angular particles are less permeable than those with rounded particles, as the permeability is inversely proportional to the specific surface. And last one is impurities of water. Any foreign matter in water has a tendency to plug the flow past and reduce the effective voids and hence the permeability of soils.